happened to your voice?
What?
Welcome back to Calculus 1.
Calculus.
Hello and welcome back to Calculus 1, section 4.6, mean value theorem.
I feel a lot better.
We don't say mean as evil value theorem. We mean mean as, in between two values. So I will write the formula first for the mean value theorem, and then we are going to take a look at the concept, the theory behind it, and then we're going to work out some problems and be done in 7 minutes. So first of all, we have the requirements that the function must be continuous and differentiable. So if function f is continuous, on closed interval a, b, and differentiable on open interval a, b, then there is at least one point C, element AB, such that, and here is the big statement, f of b minus f of a over b minus a, which is the average, equals to f prime of c, which is instantaneous. In the nutshell, what this says is that slope of the secant line is the same as the slope of the tangent line at that value c for the right. Now, thinking about a graph of this, let's say you have some kind of a function f of x, come on, y, there we go, and I will draw a tangent line and parallel to it a secant line. So these would be your A and B, the blue ones, and the red one would be C. Clearly from the formula you see that the slope of the secant is the same as the slope of the tangent line, right? The secant line is the blue one, right? Secant means to cut in Greek. And then the tangent line is one that touches the function at one point. So I have these two lines and they are parallel. This has some really cool application out there. We'll see. But I hope you see that this C must be between A and B somewhere. And I hope you also see how we can break this rule, this theorem, if you kick out either continuity or if the function is not differentiable. Then this is not guaranteed. But if those two conditions are there, then this is pretty much guaranteed. So what can I do with this? Let's see. Time for art. Ready? Here's highway. I'm going to put a bush and shrubbery over here, another bush shrubbery over here. Here's you on a highway in your car going that way. It's 65 miles per hour. Right?
Giant boat.
Don't worry about it. Because
Oh no.
The car.
It's a car. Okay.
actually, wait, I got that wrong. We'll go this way, right? If they're hidden this way.
Unless you're in London.
All right, so yes, let's say that these guys are, I don't know, 10 miles apart. So let's say they're 10 miles apart. They are using X band, which is very easy for you to detect. So you are speeding, obviously, and then your radar detector goes off. You go through the first trap at 65. You're all good. You speed off. You go to the second trap, but your alarm triggered again, so you slow down, so it's 65 again. And you go, I show them, right? Because you have your $400 radar detector. And then within a month, you get a ticket in the mail. And you go, what the hell? I drove 65 through both. I know, right? Yeah. But now cops do calculus too. All right? I don't mean calculus 2. I mean calculus 2 with 2 O's. Not with the W. So what happened here? Well, the issue is that you passed through the first gate at 1:06 p.m., right? Through the first trap at 1:06 p.m. and you were doing 65. That's good, right? And you passed through the second gate at holy nightmare, man. At 107, yeah, sure. It took you a minute to.
111. 5 minutes. 5 minutes.
No. And you pass through the second one at 1:14 p.m. Right? So now you're looking at this, right? You don't notice that, but you got the ticket in mail and you're just figuring out what the hell happened, right? So you're analyzing this. You know that the speed is distance divided by time, and you go and you say, all right, so my distance was 10 miles in between these two guys, and I had the difference of 8 minutes, so 8 over 60, right, to put that into miles per hour. Because if you put 8 minutes there, then it's miles per minute. So this is now 600 divided by 8. And what's your average?
75 miles an hour. Got it.
So that's 10 over. Now, what do you have as the theorem? The theorem says that your average is going to be equal to instantaneous somewhere if it's continuous and differentiable. Well, differentiable means you do have a speed, right? You were driving the car, and the road was continuous because you were alive on the other end. So the trip was uninterrupted. So you see that the conditions for mean value theorem are met. Now, what do cops charge you with? They charge you when they measure you, which is your instantaneous speed. Your speedometer shows instantaneous speed, which is the derivative. This theorem is the link between the average speed which you can measure in this way, and instantaneous showing that at least once those two speeds were the same. So the cops know that you at least twice went 75 miles per hour. Because think about it. If your average speed is 75 and the speed through two gates was 65, that means that you have to go over 75 so you can bring the average down. But they can't prove that. Mathematics will not allow for that proof. Mathematics allows for the proof that you were at least once driving 75 miles per hour so this ticket can be issued. Do cops do this? No. They don't. Because it's way too much coordination and so on. Easy pass. Easy pass gates, guys. You go for the first easy pass gate, the other easy pass gate is on a fixed distance. You have to pass through the first one with 25 and the second one 25 in order to read, right, the thing. If the time doesn't match up, they mail you a ticket. So easy pass gates are a very easy way to implement something like this, and that's been in research and testing and so on, and people did get tickets. But then they're thinking of actually just making a speed gate, so on. So technically, there is no way to cheat that system. Because if you are driving 60 miles per hour, that means a mile per minute. So you can drive 120 miles per hour if you want to, and then before you pass the second gate, park and wait 10 minutes, right? And then pass through the second gate and then no ticket for driving 120. You know what I mean? So there's no way to cheat this system. If you install these meters, right, and all they need to do is take, right, the red car passes and the red car passes again, right, it's the same car with the same license plate and so on. Compute, the whole thing can be automated easy. The only way that you as a driver can battle this is you swap the easy pass account, right? You have two accounts, so you swap each gate. I mean, that's possible. Or just have autonomous car. In that case, the car will not be speeding. You don't have to worry about driving. You can sleep, and the car will take care of you not getting a ticket. So, so that's one of the applications, right? Many other problems in the book. I would like to first do one of the, whatever problems, and then we'll do one more application problem, and the section is over. And we'll see what we're gonna do after. This is a very short, right? You have only one formula to worry about, and that formula is that average is equal to instantaneous. I don't know, each one of these problems is problem 20. Determine whether mean value theorem applies, and then figure out at which value we have this be true. So function f of x is equal to ln 2x, and we are on the interval 1 to e. Is it continuous? Yes. Is it differentiable? Yes. Right? So you have to check that. Is it continuous? Yes. Is it differentiable? Yes. Right? So we can differentiate, and we have continuity. So it works. So now what do I have? I have f of b minus f of a divided by b minus a equal to f prime of c, and I am looking for that c. Well, I have my a and b, that's 1 and e. I have the f of x. I can figure out that f prime is 1 over x, that's easy. So let's plug everything in. Function computed at b would be ln of 2e minus ln at 1, which is ln of 2, right, because 2 times 1, divided by e minus 1, that's denominator, is equal to 1 over x, but I need to plug in c, so 1 over c. And maybe I should just do this and that, so you know that you plug in 1 over x into derivative, but because it has to be of c, it's 1 over c instead of 1 over x. Compute this. We have ln 2 plus ln e minus ln 2 over e minus 1 is equal to 1 over c. Hopefully you know the product rule for logs, right, where the product of arguments is the addition of logs. At which point ln 2 dies. Ln e is 1, so we get 1 over e minus 1 is equal to 1 over c. If we flip one fraction, we flip the other one, so c equals to e minus 1. And that's the value. So we have c equals e minus 1. That's the answer. At that point, we have the tangent line that is the same slope as the slope of the secant line stretched between one. Now, I'm not sure how well I can draw this. I'll try. But here's my ln x. So let's say this is 1. There has to be, right? It's the x-intercept. And let's say this is e. So as you can see, I can't really draw well because these curves are not curved enough. But these two, blue line and red line, they are parallel. This value over here is e minus 1. Exaggerated, this would look like this. So red line and blue line have to be parallel because they have the same, right? We have the same slopes. Those two lines are parallel. So we can find at which point we have this. So word problems, we have 33, 34, 35, 33 mean value theorem and the police, which is what I just did. 34 mean value and the police again. I'm not joking, that's exactly how it is in the textbook. And then problem 35, running pace. So 2 problems on cups and then running after that. So let's see. Let's take a look at running because both cup problems are already solved. Running pace. Explain why, if a runner completes 6.2 mile race in 32 minutes, then he must have been running exactly 11 miles per hour. So speed had to be 11 miles per hour exactly twice. Or at least twice. Explain why, if a runner completes a 6.2 mile run race in 32 minutes, then he must have running at exactly 11 miles per hour twice, at least twice in a race.
What does that mean? Like, because he could be running 11 miles per hour for like a second, and then like twice. You know what I mean?
Well, the trick is that you have to start running at 0, and when you're done, you stop running. That's the object, is to actually finish the race, and then you don't have to run anymore. So if you start running, you will start at 0, and then when you're done running, like your car right now is parked, I hope, right? Otherwise, you don't in the morning, right, when you're ready for school, you don't have to jump into the moving vehicle, right? You don't jump into it, so it's parked.
So he needs to hit that point twice.
Yes.
Okay.
So let's see. This is the same as the cup thing up there. You have that the speed is equal to the distance divided by time. And didn't we talk about blessing for the entire 6.2 times 60, 372 divided by 32. $11.625. So you see that, right? So you see that the average speed is going to be 11. That means, and since the graph for the speed, I don't know how the graph for the speed looks like, right? It can look like whatever, but it's eventually going to stop, right? So if you start at 0, and let's say the fastest this person ever ran was 13 miles per hour, right? It hit 11 here and on its way down. It might hit 11 in many, it said at least twice, but it has to be at least twice, because you see that the average speed was 11,625. It started at 0 to build to the average, and then even more than that, because it has to average back down to 11. Right. So whatever the numbers are, but we see that definitely at least twice had that exact speed. And remember what the speed is. Speed is whatever speedometer tells you, because that's instantaneous. So when you're driving your car, right, the first thing when you see a cop is you look at your instantaneous speed, because that's what you get quoted for, right? It will take time to brake. It will take time to do anything else. So yeah, that's technically what it is. And that's the mean value theorem. This one formula that says that the average is the same as the instantaneous at one point if those two conditions hold, which is at least 1 point. You can have more.
What's the price of that? It's still like a 5-minute mile.
I wouldn't know, because I think I can run a mile very fast, so I don't consider myself with these slow speeds.
With a car, you mean?
Yeah.
Oh, yeah.
Anyone wants to race? Let's see.
Street racing after
No,
class.
you have. We're gonna go, you have.
Whoa!
Oh, howdy. No, I mean you running, me driving, not. No, I don't support street race or anything. No, absolutely not. I mean, we could race in a parking lot a mile. I'll be in my car, you'll be running, and let's see who wins. All right, so that's technically it for this time, and I will. All right, let's and we'll talk about some other stuff. I think we have